In this unit, we look at nuclear chemistry and the changes that occur in atomic nuclei during nuclear reactions. Nuclear reactions differ from other chemical processes in that in a nuclear reaction, the identities of the elements change. In addition, nuclear reactions are often accompanied by release of very large amounts of energy, as much as 1 billion times more than the energy released by chemical reactions. Nuclear chemistry also has a number of important applications, such as in medical imaging using radioisotopes, such as seen in this diagram. Radioactivity is the spontaneous disintegration of an unstable nucleus by the emission of radiation. In the image on the right, we have a picture of uranium oxide, UO2, which is used to make nuclear fuel pellets. However, many common everyday objects are naturally radioactive, such as the case of bananas, as we see here. Bananas are known to be high in potassium. However, a very small fraction of the potassium in bananas is present as the naturally occurring isotope potassium-40, which is unstable and produces a very tiny amount of radioactivity. Whereas chemical reactions involve the transfer or sharing of an electron to form compounds, leaving the nuclei unchanged, nuclear reactions involve changes to the nuclei, which often results in the formation of different elements. These nuclear reactions are often accompanied by changes in energy that are much larger than those for chemical reactions. The decaying nuclide is called the parent nucleus. The product nuclide is called the daughter nucleus. When a nuclide decays, it forms a daughter nucleus that is lower in energy, and the excess energy is carried off by emitted radiation and the recoiling nucleus. To balance nuclear reactions, both the total charge, Z, and the atomic mass, A, which is a sum of both protons and neutrons, must balance in the reactants and the products. Marie Curie was a Polish-born and naturalized French physicist and chemist who conducted pioneering research on radioactivity. She was awarded the 1903 Nobel Prize in Physics, which she shared with her husband Pierre Curie and Henri Becquerel, and the 1911 Nobel Prize in Chemistry. She is the only person who has ever received 2 Nobel Prizes in multiple sciences. Interestingly, the Nobel Committee initially intended to only honor Pierre and Henri Becquerel. However, one of the committee members was an advocate of women scientists. Swedish mathematician Magnus Gösta Mittag-Leffler alerted Pierre to the situation, and after his complaint, Marie's name was added to the nomination. Marie Curie was the first woman to be awarded a Nobel Prize. The nucleus is composed of both protons and neutrons. Together, the protons and neutrons are called nucleons. The atomic number, Z, is the number of protons in the nucleus. The mass number, A, is the sum of the protons and the neutrons in the nucleus. So we can see that we can easily calculate the number of neutrons in the nucleus by taking the mass number and subtracting the atomic number. The notation for writing symbols in nuclear chemistry is to write the mass number as a superscript and to the left of the element symbol. The atomic number is written as a subscript and to the left of the element symbol. There are a number of elementary particles in nuclear chemistry. The first one that we'll talk about is the proton, which is given the symbol P or capital H. Since a proton has a mass of 1, the mass number of the proton is 1. And since it's a proton, it has an atomic number of 1 as well. The next elementary particle is a neutron, which is given the symbol N. It has a mass number of 1, and since it's neutral, it has an atomic number of 0. The electron is given the symbol E, or the Greek letter beta. Since electrons are much lighter than protons and neutrons, electrons have a mass number of 0. And since electrons are negatively charged, they have an atomic number of -1. So here we can think of Z as being the charge for electrons The difference between the electrons here and the electrons we normally think about is that these electrons originate from the nucleus. The next elementary particle we'll look at is the positron, which we can think of as a positively charged electron. A positron is given the symbol E, or the Greek letter beta, and has a mass number of 0. However, since it's positively charged, it has an atomic number of +1. Finally, we have the alpha particle, which we can think of as the nucleus of a helium atom. As a consequence, it's given the symbol He, or the Greek letter alpha. Now, since an alpha particle is composed of 2 protons and 2 neutrons, it has a mass number of 4. And because it has 2 protons, it has an atomic number of 2. The atomic numbers and mass numbers for each of the elementary particles is also summarized at the bottom of the slide here.